Good.
Okay, great. So the next talk is by Sepehr Assadi on sublinear algorithms for delta+1 vertex coloring.
Okay, so thanks for inviting me here, and also thanks for everyone coming to this talk. So let me tell you about some sublinear algorithms for this delta+1 vertex coloring, and this is a work I've done as a graduate student at Penn with Yu Chen and Sanjeev Khan. Okay, so quick reminder, C coloring of a graph is basically an assignment of colors 1 to C to the vertices so that no edge has the same color on both its endpoints. So let's say here I have a palette of 4 colors. This is my graph, and this is showing a 4 coloring of this graph. Good. And this is a very central problem in both graph theory and computer science, and has lots of applications. And so this is the problem I'm going to talk about today. And let me use this notation that throughout this talk, delta is going to refer to the maximum degree of the graph for me, and n is going to be number of vertices. Good. Okay. So one of the very first thing you learn about graph coloring is that every graph can be colored with delta+1 colors. The reason is almost trivial because you can just greedily color the vertices, and by pigeonhole principle, you never run out of color. So here, when I want to color this vertex, even if I use a different color for all its neighbors, I still have one color here, red, to assign to this vertex. Good. So delta+1 coloring have this amazingly simple textbook greedy algorithm. It's extremely efficient. It's linear time and space. And it's still in some scenarios, even such an algorithm is not, we won't be able to use such an algorithm when our graphs are large enough. And so you may want to ask it, are there even more efficient algorithms for this problem? This is basically the area of sublinear algorithms that answer this question. So maybe I want to try to solve my problem by reading just even faster than reading the entire input, by just querying it at some appropriate places. Or maybe I want to solve my problem without even storing the input, just at the same time that the graph is being generated, I want to just process it on the fly and solve the problem. Or perhaps my input is so large that I cannot even store it in one place. It resides on many, many distributed machines, and then they want to solve it with limited communication in parallel. So these are some models of sublinear algorithms that I'm going to talk about. And this was basically the motivating question behind our work. Is there a way to design sublinear algorithms for delta+1 vertex coloring? Now let me say something here that if you work on sublinear algorithms, or at least for us, there was this strong bias that the answer should be no to this problem. Let me give you some reason. One informal reason is that if I look at similar problems to this problem, let's say MIS or maximal matching, classically, both of these problems are solved effectively by the same greedy algorithm. But we could show that, for instance, neither of these problems admits sublinear time algorithm, or MIS doesn't have a streaming algorithm. And in fact, even maximal matching doesn't have a streaming algorithm when you allow edge deletion from the string. Okay. Good. So this is one reason similar problems were hard. And this was the informal reason. Now there is even a more informal reason. The motto of sublinear algorithms is basically that we want to get something for almost nothing. Okay? And here the emphasis is on the something part. It basically means that in sublinear algorithms, we are usually settling for approximation. But here delta+1 coloring, at least in some cases, is tight. Okay, so we don't want to allow for any approximation. Okay, so sounds good. So now with this in mind, let me tell you a result. Well, it turns out that surprisingly, actually, this bias was not true, and we were able to design efficient sublinear algorithms for delta+1 coloring in all of these models. Let me mention the algorithm. For instance, we were able to give an algorithm that runs as n to the 3½ time if you give it the adjacency list and matrix of the graph. Okay? And if you see for moderately dense graph, this is even faster than reading the entire input. For instance, in the streaming model, we could give an algorithm that uses a space O tilde n proportional to the output size, which is definitely necessary, and just makes a single pass over the input. And similarly, in this parallel MPC model, we have an algorithm that uses literally just one round and requires O tilde n memory per machine. Good. So now one thing I should clarify here, these algorithms are all randomized. With high probability, they output a valid delta plus one coloring, and otherwise they output that they failed. They never output a wrong coloring. And also previously, basically nothing was known in this regime. We didn't know any non-trivial single pass streaming algorithm or sublinear time, and no constant round MPC algorithms. And finally, for the second two results, it sounds like this looks like optimum bonds. But even for the first one, this is not an arbitrary number. We are able to show that, in fact, you need n root n time to solve the graph coloring problem, even if you want to do 2 delta coloring, for instance. Okay, so this was our results. But in fact, the main result of this paper was something entirely different. It was just a structural insight into the delta plus one coloring. It's just a simple statement, which we call palette sparsification theorem. It says the following: let's, for every vertex of the graph, independently and uniformly at random, sample order log n colors from 1 to delta plus 1. Okay. Then I claim that with high probability, we can color graph G by using just these lists of color for vertices, or in other words, G is least colorable from these lists. Let me show you an example. Let's say this is the original graph. In original delta plus one coloring, every vertex has this palette of size 6 to color the graph, and we can choose the color of each vertex from such palettes. What we proved that is that you can take these large palettes and shrink them down independently across the vertices to different palettes of size order log n. Okay, let me emphasize, these palettes are going to be chosen independently across the vertices. Okay. And now with even this much smaller palette, we can still color the graph. Okay, good. So this was basically the main result of our paper. And I mean, it sounds like an interesting result on its own, but why is such a thing useful? Let me give you a very quick argument. It's going to give us some meta algorithm for delta plus one coloring. The algorithm is the following. Before even you see your graph, for every vertex, sample these order log n colors, and then look at any edge. And if the lists on its two endpoints do not intersect with each other, throw that edge out. That edge is never going to be important for us in terms of coloring anymore. Now let me call the remainder graph the conflict graph. And in this graph, it's very easy to see that there are only going to be n polylog n edges. The reason is that we start with n delta edges, and two lists of size log n are going to intersect with each other. The two random lists of size log n from a universe of roughly delta are going to intersect with each other only with probability log square n over delta. And if you multiply these numbers, we get this bounded. This graph is going to be very sparse. So now we have this situation that instead of coloring the original graph, I have a much sparser graph. And because I chose the color of all vertices from 1 to delta plus 1, if I list color this sparser graph, I actually get a delta plus 1 coloring of the original. Now this seems good at this point. The only problem is that there's absolutely no reason a priori that I should be able to list color a graph with just lists of size log n. And in fact, it's easy to see that maximum degree here is around log square n. Okay, so none of this, it's not at all obvious that we should be able to do the list coloring. But that's what this palette sparsification result is saying. It says that no, in fact, even though the lists have become much smaller, the graph is much sparser, we can still color the graph using this list. This is basically the algorithm we are going to use everywhere. And why this is useful is that we have started with a graph with n delta edges, and now we can just reduce the number of edges to O tilde n and still color the graph. And at the same time, the way we sparsified the graph was we never really had to look at the graph to choose these colors. These sparsification results are extremely helpful when you want to design a sublinear algorithm. Okay. Sounds good? Good. Okay, so now let me tell you a bit about how did we prove this palette sparsification theorem and what are some ideas behind. And basically the main insight or an easy step at the beginning is to let's reformulate coloring as an assignment problem. Let me show you this through an example. Let's say I want to color this 6 clique, a clique on 6 vertices. I'm going to turn it into this complete bipartite graph. I write the vertices of the graph on the left and the colors on the right, and then I'll add every edge. And delta plus 1 coloring is basically the problem of finding a perfect matching in this complete bipartite graph. Let me call it a palette graph. When you find a matching, you'll just come back and here color the vertices accordingly. So that's delta plus 1 coloring. What is palette sparsification? So we start with this palette graph and we sample log n colors for each vertex. So we get a random bipartite graph here where the degree of vertices on the left is log n. And to prove palette sparsification for cliques, the only thing we need to show is that such a random bipartite graph has a perfect matching. But this is basically random graph theory 101. We know that this is true by very simple results. Okay? So that's the entire proof for showing the on cliques palette sparsification works. Now, in general, we can reformulate the problem as finding this G coloring subgraph. If you give me any G, which is even not a clique, the assignment problem will be the following. So let's say this is my graph. I want to find an assignment of vertices on the left to the right so that every vertex on the left is assigned to at least one color. And a vertex on the right, if it's assigned more than one color, those vertices, let's look at the green, those vertices should form an independent set in the original graph. Okay, so that's the assignment problem for the general graph coloring problem. And with this view, palette sparsification is basically just a random graph theory question. If I give you a graph G, is it the case that a random bipartite graph contains a coloring subgraph for this graph G or not? And even though the definition might be a bit hard at this point, it's a very, very useful reformulation when we want to prove palette sparsification when G is almost a clique. So it's a clique minus an edge or a clique minus a matching and things like that. Because the structure of G is this coloring subgraph for G, I have a simple structure. But in fact, this is not at all a good formulation when I want to work with graphs which are very far from clique, because then these coloring subgraphs turn into something very chaotic. Okay, no problem. So how do we handle the case of the graphs which are far from clique? And as an example, let me show you how we are going to handle them for low degree graphs. So let's say that I have a graph which all of its vertices have degree less than delta over 2, and it's still, okay, there is one vertex of degree delta. So here I claim that palette sparsification is a very simple argument. In fact, let's just open the colors of vertices one by one. Let's look at the first sample colors of each vertex. There is a good chance that we can color a vertex with that color if it doesn't appear in its neighborhood. So let's say in this picture, I can color these two vertices. If I could, and I couldn't color these two because they both sampled the blue color. So I wait and I look at the second colors I sampled for the vertices. And then if this color was unique in its neighborhood, I'm going to assign. And the reason this is helpful is that if degree of every vertex is delta over 2 and I sample from delta colors, at every step I have a probability of at least half to color the graph. So after order log n steps or after having lists of size log n, I'm able to color the entire graph. So for coloring the low degree graphs, this is actually quite easy. So now what is the general proof? we saw that we can handle the problem when this I have clicks as my input. We can handle the problem when I have low degree graphs. In general, we have to interpolate between these two. And the problem is that neither of these proofs are suitable for handling the other one. This assignment proof that I showed you is really hard to work with when I want to work with low degree graphs, because the structure of G becomes very complicated. And at the same time, the greedy simulation basically just doesn't work for coloring the clicks. That underlying greedy algorithm that I showed you requires roughly delta rounds for coloring the click. So how do we handle this? We are going to decompose our graph into dense and sparse regimes. Dense parts we are going to apply the argument for clicks, and sparse part, we are going to apply the argument for low degree graphs. And in fact, this is similar to some classical works in graph theory, such as work of Reed on extending Brooks' theorem to other settings.
Sepehr, there's a question in the meantime. So
Sure.
Akash Kumar is asking if we can shrink the palette size further and produce palettes of size smaller than log n.
Good question. No, omega log n is necessary also. If you just have a, let's say, collection of disjoint clicks of size log n, you also need to sample log n colors. Okay, so yeah, so the plan is to decompose the graph into dense and sparse parts. And for that, we are going to use this decomposition results of Harris, Schneider, and Su, which is using distributed delta plus 1 coloring, and we're going to extend it to something slightly different. And in fact, this decomposition, and again, this approach, are in general based on this sparse dense decomposition used in graph theory. So the version of the decomposition we are going to use is going to be something like this. Any graph G for any parameter epsilon can be decomposed into these two sets of vertices. We have a sparse vertices that in their neighborhoods, there are a lot of missing edges. There are, let's say, epsilon delta square non-edges among their neighbors. So the neighbors are very far from being a click. And any vertex which is not that is part of something which is really, really similar to a click. Let me just say that it's epsilon close to delta plus 1 click in a property testing sense, meaning that we have to change epsilon. If we change less than epsilon fraction of its vertices and edges, it turns into an actual delta plus 1. So as an example, basically any graph, it can be seen that these are its sparse vertices. Their neighborhoods are very different from a click individually. And these are the dense part. They are themselves almost a delta plus 1 click. Okay. And so now let me have this decomposition. And with this decomposition, we are going to prove our theorem as follows. Remember, we want to show that for every vertex, if we sample order log n colors, we can still color the graph. So we are going to start with this decomposition, set this parameter epsilon to be something like 1/1000, or even maybe something slightly bigger. And then I'm going to first look at the first half of the colors I sample for vertices and use that to color all the sparse vertices. And this part is more or less the same greedy argument as before, using some standard ideas. The main part is now to color the almost clicks in this decomposition. And for that, we are going to go over them one by one. Assume that you colored everything outside the almost click, even adversarially, and use this assignment reformulation that we have to color this almost click using the random colors we sample for vertices. And just as an illustration, again, we start with this graph, we do the decomposition, we can color the sparse vertices easily, and now I want to color this almost click here. So I have to color a structure like this. And you remember the palette graph that we created. The only difference now is that some colors are already ruled out. So this vertex is not going to have an edge to the blue vertex anymore. And the key technical lemma that we proved in this paper was that if I look at these partial palette graphs of these almost clicks, and then I sample order log n colors for vertices from that graph, we are going to be able to still find these coloring subgraphs with high probability. And I will not get into the proof here, but let me just mention that there are two challenges of doing this thing. One is that this is no longer really a random graph because some edges to begin with cannot be part of this graph anymore. But the good thing is that because we start with an almost click, the number of those edges is not that much.
So, sorry, Sepehr, could you, I might have missed this, but the almost click, is that for you the graph where every vertex misses at least an epsilon? Oh, every neighborhood is missing at least epsilon squared, delta squared?
No, almost.
Like the other side.
This object is epsilon close to being a delta plus one click.
Okay. So in the sense that you have to, you can turn it into a clique by removing at most epsilon delta squared edges or so.
Or adding epsilon delta square edges, or actually it's a bit more strict, is that every vertex has at most epsilon delta neighbors outside this object, at most epsilon delta non-neighbors inside. Okay, and these epsilons, okay, these are some constants that I'm hiding. Make sense?
Yep, thanks.
Good. Okay. So there were two problems with handling this thing. One was that this wasn't really a random graph. The other thing is that these coloring subgraphs are not necessarily a perfect matching. They can be something up to 2-factor, but both of these things can be handled and we can color this almost click. And then the proof is done basically because we can color each of these almost clicks individually. So we color this one, we color this one, and then we are done. So basically that's the proof for palette sparsification. And now let me move on to quickly tell you how does the sublinear algorithms work. Well, all of our algorithms are just using that meta algorithm I told you. We find this conflict graph and then we least color the conflict graph. And let me not get into it, but it's very, very easy to find the conflict graph in all of these models. Okay, if you think about it, you can just do it on your own pretty quickly. So now the good thing is that conflict graph has all the information we want to do the list coloring. There's only one problem, that all these things that I talked about were information theoretic. I never talk about computation. And the catch is that list coloring with order log n colors in general is NP hard. So I cannot just say that go ahead and list color it if I want an efficient algorithm. So we have to turn this proof into an algorithm and get an algorithmic proof. And it's not hard to do that, in fact, if you give me the decomposition. So given the decomposition, there is the original proof gives an algorithm that can color the graph in n to the n root n time. And in fact, more recently, we can show that we can do this thing even in O tilde n time. But then this means that we also, if I want to have an algorithm which runs in efficient time, we also have to be able to find the decomposition. And for that, we have to work with some approximate version of the decomposition. And so basically, we design some sublinear algorithms that find the decomposition, and then based on that, we can solve the problem. Good. Okay. So yes, let me quickly conclude. So there have been a lot of development on these problems after our work. There's this nice work by Chang et al. That give even more sublinear algorithms for delta plus one coloring. With Shai Solomon, we designed some maximal independence set and matching algorithms for bounded neighborhood independence graph. And these have been recently improved to 1 plus epsilon approximate matchings. Vera, Chakraborty, and Ghosh give similar result as ours, but this time based on degeneracy of the graph. They show that you can get something like kappa plus a small o of kappa algorithm, like coloring algorithms in these models. And at the same time, unlike delta plus one coloring, kappa plus one coloring is hard in these models. And then more recently with Nogalon, we showed that we look at palette sparsification as a problem on its own, and we look at some extensions to triangle-free graphs or degree plus one coloring. And again, this gives us a lot of sublinear algorithms as well. One other line of work is that all of these results that I mentioned are randomized algorithms. There are some nice recent works on deterministic sublinear algorithms in MPC model for this problem. And finally, more recently, I've been looking into, can we get some result for delta coloring in this model? Here, most of the results are lower bound, but it seems that there you can do also non-trivial things, even for delta coloring. Good. Okay. So let me quickly wrap up here. The main result of our paper was this palette sparsification. It's easy on clicks, easy on low degree graphs. And then we use this decomposition to interpolate between these two. And the main challenge here was to do random graph theory and graphs which are not so random. And this, using this route will give us our sublinear algorithms information theoretically, but to make them computationally, we had to also design some sublinear algorithms for finding decomposition, etc., etc. And that's it, basically. This is the list of the main results we got from this, and most of these results are optimal in their models as well. That's all I wanted to say. Thank you.
Right, thanks, Sepehr, for the great talk. So there have been some questions in the chat, but you have answered all of them in the meantime, I think. Okay, good. So Thashafol asks, could you mention some more applications of sparse dense, sort of the HSS decomposition, say in the centralized or classical setting?
So good. So the HSS decomposition, I know it's been used in distributed computing, for instance, to design local algorithms for delta plus one coloring. There is that line of work there. There is also in classical setting, or let's not even say classical, in graph theory, people have looked at this type of decomposition to prove extensions of Brooks' theorem, for instance. For instance, they've proved that every graph can be colored even with delta minus one colors if it is not, if delta is sufficiently large and if this is not a clique, for instance. Or there are some results for proving frugal coloring. You can find a delta plus one coloring such that no colors appear more than log delta over log delta in the neighborhood of each vertex. Okay, those type of things have been, these type of decomposition have been used to prove those results.
Okay, good. So we are running a bit late, so perhaps let's take the other questions on Slack, and thanks again for the great talk.